Hello, welcome to our series of lectures on Verilog procedural blocks. In particular, we're going to talk about the always block. We'll start out by talking about number representation and what concatenation means. We'll talk about our two different data type groups, wire and reg, and then we'll get into using the always block in circuits. You may have already seen examples of always blocks in our lecture on multiplexers and decoders. I showed some examples of that. Right, this is more or less about the Verilog syntax. What are the rules to write these Verilog modules correctly? Right. So number representation, right? Verilog has a 4-value system. Based on our binary system, 0 represents a logic 0, 1 a logic 1, Z is a high impedance state, which we won't work with. We haven't gotten any circuits yet that can use that. And you can use X for don't cares. We likely will not be using those as well in this logic design course. Right, so we'll concentrate on the zeros and the ones. We want to know how to properly represent an integer constant inside a Verilog module, and there's a general form. Right, the general form is we have the sign of the number. Now, when we write a positive number, we generally don't put a plus sign. The next then field is the size, and that's the size of the number of bits, and it has to be followed by the apostrophe sign. After that, when we write an integer constant number, right, we specify the base that we're writing in, and then we actually write the number value. And these brackets mean that technically all of these fields are optional. Right. When we specify the base, right, we can say that it's binary, octal, or hexadecimal. Right, by using then an upper or lowercase, B for binary, O for octal, H for hexadecimal, D for decimal. Now, if we don't specify a base term, it's going to assume that whatever number constant we write is in decimal base 10 format. And so we'll see then, right, whenever we use the size term, right, it will be considered a size number. It'll know how many bits to use. If we leave off the size term, it'll be considered an unsized number. So for unsized number, the actual size will depend on the host computer, but it's going to be at least 32 bits. Like I said, a size number specifies the number of bits explicitly. If the size of the value is smaller than the size term specified, zeros are padded to the front to extend the number. In other words, if you think of the binary number 1, you only need 1 bit to represent that. And so if you say this is a 4-bit number, it's just going to put then those 3 missing bits, will all be zeros padded to the left. We don't have to worry about the Z or the X. Right. And this pretty much covers what that just said, so let's not dwell on that. Let's actually then move on to here a few examples of how to write then size numbers. Notice then this first example, there's no sign out front, so it's going to assume that it's a positive number. Then here, the 5 says that I want 5 bits to represent the number. The apostrophe is part of the syntax. The B says I'm going to write in binary, that the constant value I write after this is in binary. So the constant value then is 11010. And so when I say stored memory, what I'm saying is when we write this out, we're going to assign it to some sort of variable, and this is what will be stored in that variable's memory. You can also, if a number gets really long, you can break it up with underscores. So in this case, this is still a 5-bit binary number, right? It's just simply saying this underscore says I'm breaking this up to make it human readable. The underscores ignored, we still get the 11010. But if you could imagine if you were trying to write out some sort of 32-bit number in binary, you probably want to break up the fields into 4-bit nibbles, right, to make it more readable. Right. If I write this number constant, and here again 5 bits, but now it says my base is octal, and an octal 32. Well, an octal 32 translates to binary, because remember, it's going to store everything in binary, right, to the same number, 11010. Similarly, we can say it's a 5-bit hexadecimal number, 1A. Well, 1A translates to binary as 11010. Right. lastly, if we write the same thing as a decimal number, I can say it's a 5-bit decimal 26 translates to the binary. So you can see that all of these represent the same stored value. There are just different ways you can write it. And you're obviously going to write it in whatever way you're most comfortable with, whatever way makes most sense to you. Most of the time, I will write things in binary or hex, simply because we're working in binary. It's really easy for me if I write out the pattern, right, to know what should be stored there. If I write something out in decimal and I have to go back later and try to convert it in my head, or probably shouldn't convert it in my head on a piece of paper, that's extra work I need to do. So I often do the conversion ahead of time if I've got decimal numbers to binary and write out the pattern. But that's usually because I'm working with something that is 8 bits or smaller. If I was working with 64-bit numbers, I might actually use hex or decimal. All right, so here are examples then when we talked about the 0 padding. So if I want a 5-bit binary 0, again, here's my size, apostrophe is required, B stands for binary, 0. Well, the 0 only takes up 1 bit, so that's this bit. So 0 extended means then that Verilog will just go ahead and append, right, these 4 zeros out to the left. Doesn't change the value of our number. Same way, a 5-bit binary 1, well, this would look like this in memory, right? The 4 zeros and the 1. So these are our least significant bits. It's going to pad with zeros. And so we're not going to worry about the z's and the x's, right? Here's the other thing that you'll find handy. If you have a negative number, if you want to represent a -1, well, here I put the negative sign in front, 5 bits, binary, and I wrote out 001. It could have just been plain old 1. It will actually store it in 2's complement form, right? So I can write this with the magnitude that I want, -1, and it will actually then change it to 2's complement form. So we don't need to do that, right, manually. Now, for an unsized number, right, if we don't specify how many bits we want, then, right, it will actually then extend this out to 32. So here, we can have this apostrophe with no size. Say that I'm writing in binary, give the pattern. Here's my binary pattern. Because I didn't give it a size, it extends everything out to 32. When we're creating hardware, our hardware has physical size limitations. So most of the time we do not use an unsized number. We want to specify the size. Same thing, this would be an unsized hex number. So hex EE, well, there's EE, and it just extends the rest out to zeros. We just plain old write the number 1, which I sometimes forget if I haven't been writing in Verilog for a while. I'll just write one of these constants. Oh, it's the number 1. And later, as I'm checking my circuit, I'll see this 32-bit number and go, oh, I forgot to specify the size. Same way, -1, it will then convert that to a 2's complement 32-bit number. So you want to be careful about when you use size or unsized constants. All right, let's actually then take a look at what we mean by concatenation. Right. So concatenation actually then, so the concatenation operator are these 2 curly brackets, a left and a right. And it's going to combine segments of elements in small arrays to form a larger array. Well, what that means is it's going to take, we can take pieces, right? Remember, anything that we have in an array is also known as a bus, is a single wire. We can take different groups of wires and combine them together to form a bus. And so here are some examples, right? And so if we declare A, B, and C as just a wire type, right, these are all single bits. Here, I'm also declaring that there's going to be 2 buses, bus 1 and bus 2. They're all 3 bits wide, so 2 down to 0. Each one of these signal names is 3 bits wide. And then bus D here that I'm declaring as a wire is 4 bits wide, 3 down to 0. If I want to assign to bus 1 these individual wires, I need to form them into a group. If I use the name bus 1, that refers to 3 wires, simply because we said the name bus 1 is 3. So if we use this name bus 1 all by itself, we're referring to these 3 wires. And so if I use the concatenation symbol here and put the signals inside that I want to concatenate, the leftmost one will be the most significant bit. So what will happen is, right, bus 1 at index 2 will get the value of A. Bus 1 at index 1 gets the value of B. Bus 1 at index 0 gets the value of C. C is your least significant bit. So whatever is over here on the right is your least significant bit, leftmost, your most significant bit. And so that's how I combine single wires. Now for bus 2, again, if we just use the name bus 2 all by itself, as we are here, then that refers to a 3-bit bus. And what I can do is I can say, well, I want to take a couple of the bits from D. So I just happen to choose then bits 3 and 2, 3 down to 2. So that would be D3, D2, and concatenate that with C to form a 3-bit bus and wire that into bus 2. All right. Sorry. The last example then, right, I could say D at index 2 down to 0. So I've chosen 3 bits of D. So I don't have to choose all of D. If I just use the name D all by itself, that refers to a 4-bit bus. But here I say I'm referring to D, but I'm only referring to wires 2, 1, and 0. Right? And here I can actually assign then this constant a 2-bit binary 1, 1. Well, that means D2 is going to get a value of 1, D1 will get a value of 1, and then D0 will get the value of A. So I'm wiring A into that bus. So there are times in Verilog where we find concatenation to be useful. Actually, let's take a look at an example. All right. All right. So what if we wanted to create an XOR gate? All right. We know that we could simply, if we were trying to write a module here for Verilog, use bitwise operators for XOR, and maybe I should remind you of the XOR truth table. We have seen this in other examples, but let's take a look. So A is my input. A and B are the inputs. F is the output. Well, we know that 0 XORed with 0 gives us a 0. 0 XORed with 1 gives us a 1. 1 XORed with 0 gives us a 1. And finally then 1 XORed with 1 gives us a 0. All right. There are different ways we could solve this. We could say assign to F. Well, if we did the canonical sum of products, that is not A, AND with B, OR with A, AND with not B, right? That's our canonical sum of products form. But we could just use the XOR gate and say F is A XORed with B, right? Now we would obviously we wouldn't put both of these in here, one or the other, right? And so we then call these continuous assignment statements, right? They tend to use when they're single bit numbers with these bitwise operators. So these are our bitwise operators for not, and, or. They tend to form, like I said, when these are single bits, these tend to form the same gates that we've just specified here, right? Well, another way we could create an XOR gate is with a case statement. And in order to do that, we then need to use our always block, which we've not gotten to that syntax yet, but it starts with the keyword always. We're going to have at, and inside the parentheses, we have a sensitivity list. Well, what goes in the sensitivity list is this block is going to generate basically our output F. And so any signals that can affect the output need to go into the sensitivity list, right? Because they can change what comes out of the circuit. Right. And I'm going to put a begin and an end for my always block here. And so we have a case statement. And if I wanted to evaluate then A and B, so I'm going to leave this blank for just a second. What the case statement does with something like the XOR gate is we write something that looks very similar to the truth table. Right? So in one case, we can say, well, when our input is a 2-bit binary 0, 0, we want our output F. And I'm going to make a signal called a reg type. I'm going to call that RF. And in here, I want to assign to RF then the value of a 1-bit binary 0. All right, so our truth table says, right, whenever our input is 0, 0, F, the output F is a 0. All right, whenever we work with an always block, right, keyword always, we've got the symbol at here. Inside the parentheses, we have our sensitivity list. Well, our output F is going to be sensitive to changes on the input of A, input of B. That's what goes in the sensitivity list. Right. What we want to have here inside the case statement is, right, our output F is going to be sensitive to changes sensitive to changes A and B. But we need to then, what we're specifying on the left here is whatever the value inside here happens to be. Well, we can't just write A comma B, because what we have to write here is we need to look for a signal that's 2 bits wide. And this won't convert A comma B into 2 bits wide unless we use a concatenation operator. So the concatenation operator, right, these curly brackets, then says form a 2-bit signal, A and B, right, where A is the most significant bit, B is the least significant bit because they order from left to right. And then evaluate when those 2 bits are both 0, then we want our signal RF to be assigned the value of 0. Now, we had to create in here the signal RF because whenever we're inside an always block and perform assignment, so the equal sign is the assignment operator. Whenever we assign this value to the signal on the left-hand side of an assignment statement inside an always block always has to be a reg type. That's why we had to create this reg type here. And what we need to do out here is we need to assign to our output F the value of the reg type. I'm going to go ahead, put those in comments here. All right. So whenever we have an always block, we're usually always going to have a reg type. A reg type just is internal memory. It's internal to this module. It doesn't connect to the outside world because this does not necessarily connect to the outside world and make physical hardware. You always have to assign the reg to whatever connection you want to connect to outside the circuit. Right, so we would assign this to our output F. And then finishing up this case statement, right? We just write the rest of the truth table for the XOR gate. Our next set of inputs could be 0, 1. We don't have to do it in the order of the truth table. It's just easier for me if I do it, so I don't in the same order, so we don't skip over anything. Right, so whenever our input AB 0, 1, well, we said our output should be A1. Right, when our input is a 2-bit binary 1, 0, our output RF should be a 1-bit binary 1. And then, right, whenever our input B1, 1, our output should be a 1-bit binary 0. And then we need an end case statement. So you have case, end case. Like I said, what goes inside the case is the signal you want to evaluate. And here are all the possible values of that signal. So basically, you can think of a case statement as a way to rewrite the truth table. Let's just go ahead and save this and synthesize it to see what circuit it makes for us. Remember, for Quartus, I have to save the file with the same name as the module. Oh, I forgot to make that the top level. File set as top level. So it was throwing an error. I called the project always. It was throwing an error called always that was related to the project name, not the always statement. It's because I forgot to make this module the top level. Whenever you have a module that's a different name than what you've named the project, you have to make sure you tell it what this top level is. Otherwise, it will assume it's the project name. All right, so let's make a simulation. No, actually, sorry, I didn't want the simulation. I wanted to say tools, netlist viewers, RTL viewer to show what kind of circuit it makes. And what it actually did for A and B, it actually made a decoder circuit. So as I've said in another lecture on case statements form decoder circuits. Right, so here are 2 bits of input. Notice it gave a 4-bit output. So if you've not seen the lecture on decoders yet, a 2-input decoder always has 4 outputs. It's called the 2 to 4 decoder. That's why it shows 4 outputs here. This is using a 2 to 4 decoder for our circuit, our simple XOR gate, but it's only using bits 3 and 0 is what it's decided on its own to use bits 3 and 0 of the decoder for its output. It's putting that into an OR gate and then it's inverting it. That's quite the circuit there for our simple XOR gate. So that's the thing about behavioral Verilog. You can see that creating an XOR gate with a case statement is not a smart thing to do. That's a lot more hardware, a lot more transistor resources that this would take, logic gates to form this. Right. The reason I wanted to show it to you is to show you a circuit, right, that you're familiar with and how to put this in the syntax, right, the new syntax that we're going to be using. Obviously, we're not going to be creating XOR gates. My other purpose here was really to show you the concatenation operator, right? Like I said, there will be times then when you will find that your signal, your bus widths don't match up. You will need to use the concatenation operator to create the correct sort of signal to wire things together. All right. And finally then, let's go on with then our data type groups, which we've already basically seen, is we have 2 groups, right? We have registers and nets. Well, a net is simply a wire data type. The register is the reg data type. There are other data types within these groups, but these are the 2 we'll use. So all you really need to remember is we use wires to work with physical hardware. Regs are internal to a module. We use them whenever we create an always block. So if you've got an always block in your module, you're going to need a reg type to store information in, right? So they differ in the way that they're assigned and hold values, and they represent different hardware structures. Like I said, a wire type, you can think of this as being physically wired together. A reg, you can think of as some sort of internal memory, some variable type. It doesn't necessarily form the hardware you would expect, and it does not connect to other signals outside the module. So you couldn't use, theoretically, you're not supposed to use the reg as an output type. All right. So this is what I was just saying, that a net group represents physical connections between hardware components, wires. A net data type doesn't typically store a value, right? It's just a wire that transports that value along the wire. It derives its value from the circuit driving it. So the circuit that it's connected to, that's what circuit decides what value goes on the wire or what voltage level. Right? We use the wire outputs in continuous assignment statements, right? Continuous assignment statement is the keyword assign. Let's see, we've already seen how to create wire types in another lecture, so I won't dwell on that. We won't work with 2D arrays. All right, our other data type is the net data, our data type, net data type, wire, most commonly used. Here's another type called trie that we won't work with. So I should probably pull these out of this lecture deck if we're not working with them. Right. Our other data type group, the variable type, that's the register type. So reg variables store their values between assignments. Right. There's other data types such as integer, real, time, and real time. These data types are often used with simulation. You can write Verilog modules called test benches, which are used to then drive other Verilog modules in functional and timing simulations. That's typically where you'll use those types, but we will use wire and reg. Right. When we declare, right, a reg type, just like a wire type, we use the keyword reg, but just like a wire type, right, whenever we just write a signal name, it's 1 bit. If you need it to be multiple bits, then you specify the size out to the left of the name when you declare it. All right, let's take a look then at the always block. Like I said, it facilitates system behavioral modeling. Well, by that, we just wrote an always block that has a truth table in it. That's behavioral modeling of that truth table. We didn't have to derive any Boolean equations. We just said, here's the behavior we want. We put that behavior in there. All right. Procedural statements are executed in sequence. So this is something that's a little bit, that's different, right? When we use our bitwise operators with assignment statements, those execute concurrently. Right? There is no, we can write those in any order if we have multiple ones inside of our modules. Right. So we'll see what we mean by a blocking procedural statement, how to write an if statement, how to write a case statement. One thing you want to remember is well-written procedural code in an always block is synthesizable into hardware. You always have to think about what you're writing. You need to think of the kind of hardware you might be generating, because remember, you are generating hardware. And if you start writing some of this code in a way that looks like, if you've written any C, C++, software programming, you can write code in a way that it actually can't synthesize it into hardware. If you don't think about when you write your code, what hardware it should represent, you can write something that's a real mess. And when you run analysis and synthesis, it will come back and tell you it can't synthesize it into hardware. Then you will have to figure out how to fix it. All right, so the basic syntax of an always block, right? Keyword always, at, and inside parentheses, sensitivity list. Right? You can leave the parentheses blank, meaning that this block is sensitive to all of your inputs. Right? We typically do not leave it blank. You want to declare what it should be sensitive to. So begin and end, right? You can put labels out here next to a begin block if you want. Sometimes people put a label there to give it the name of the circuit that they're implementing, because we can actually have more than one always block inside a module. That's usually when that's done. You can declare variables locally inside here. We will not do that. By procedural statement, well, those were those assignment statements that we've seen. All right. All right. So an always block, as the name suggests, executes always, sort of like an infinite loop. It's always, always, always running. Right. Sensitivity list lists the signals and events to which the block responds. So by events, next after this, our next topic will be signals that are based on clocks, sequential signals, and it might be based on the edge of a clock, so that's an event. When any signal in the sensitivity list changes, the circuit hardware created by the synthesized code in the body of the always block is activated and executes the internal procedural statements. Right, if we go back to here, our chorus example, what this is saying is, right, if the value on either one of these signals changes, then basically it's saying that this code activates and runs to generate the change in the output signal RF, which then when RF changes, well, because RF is continuously wired to F, your output to your outside world, F will change. That is what that is trying to tell you. All right. So we can put, you can use bitwise operators inside of an always block. We don't often do that. If we could write a statement that looks something like A ended with B and assign that to F, we would just use continuous assignment. Purpose of this slide is to say that, right, I said that an always block has a begin and an end. Whenever you have a single statement inside an always block, you do not have to have the begin and end. If you leave off the begin and end, it assumes that the one statement following this is the statement that goes with the always block. We tend to indent code inside an always block to make it more readable, but just because you've indented something does not mean that it goes with the always block. As you're starting out, I would encourage you to always put your begin and end here and write your code in between so it's very clear as to what code should go inside this block and be associated with the always statement. But likely you'll see examples from time to time that I write, or you might see out on the internet where they've only got this one statement and you'll wonder why they don't have a begin and end. Right. Inside then this always block, we can have two different kinds of assignment statements, right, a blocking and a non-blocking. So by blocking assignment, so whenever you use the equal sign all by itself, that is known as a blocking assignment. Right. What goes on the right is some sort of expression. It can be a wire, it could be a Boolean expression, it could be a mathematical expression, right? Any sort of wire or reg type expressions can go on the right of a blocking assignment statement. On the left of a blocking assignment statement, this has to be a reg type. Right. So variable name, it needs to be a reg type, and whatever this expression will be assigned to this on the left. So assignment goes from right to left. Evaluate the expression, assign it to this. Non-blocking assignment, we will take a look at this when we get into clock-driven circuits. Whenever we have a clock-driven circuit, we want to use a non-blocking assignment statement. It's particularly important when we have multiple assignments going on. And we'll talk about that when we get there. So general rule, use blocking assignments for a combinational circuit, right? Combinational circuit is a circuit that is not driven by a clock. Use non-blocking assignments for a sequential circuit. That's a clock-driven circuit. So if you have a clock signal in your sensitivity list, you need to use non-blocking assignment statements. Otherwise, if you don't, you use the blocking. All right, we'll take a look at some examples of always blocks that implement combinational circuits. This is not something we typically write. It's more or less an example to give you an idea of what we mean by blocking. All right, so here's this module named temp. It has 4 input signals, A, B, C, and D. It has 1 output signal, Z out. It has 3 reg signals, X, Y, and Z in here. So the way then this block works, always at A, B, C, D. So whenever this is sensitive to changes in the input, begin and end block in here, this says, go ahead and take A ended with B and assign it to Y. Take C ended with D, assign it to X, and then or X and Y together and assign it to Z. Outside the always block, we have a continuous assignment statement where we assign then the reg type to the wire type. And so basically, right, what this signal Z out is getting, well, it's getting A ended with B, X's value is C ended with D, ORed with Y, Y's value is A ended with B. So basically, we're writing an expression that is Z is equal to C ended with D, ORed with A ended with B, which, like I said, we normally just write a continuous assignment statement with this. The reason we're doing this in here is what we mean by a blocking assignment is now order is important. So inside this always block, inside the begin and the end, what we mean by blocking assignment is it goes in order from top to bottom. So this first statement, it will evaluate A ended with B and assign that to Y. When that is done, it then performs C ended with D and assigns it to X. When that is done, then it will OR X and Y and assign that to Z, right? Because these don't happen concurrently, this takes some extra time, right? Writing something like this would take more time in your circuit, right? And then the other thing, of course, is because order is important, you don't want to have z equal x or y up here at the top. If you did, you'd be assigning values to z without performing the A ANDed with B or the C ANDed with D. So when one of these inputs changed, you'd be outputting an incorrect output. Right? So the important thing to know is, like I said, really you want to try to avoid writing circuits like this, right? Anything you can write with a bitwise operator and some simple gates, we tend to do that. But as we move forward and start writing things that are a little more complex in nature, you need to be aware of the fact that these are blocking, these will be performed in order. If your order is incorrect, your output will not be what you expect. Right. So here's an example, right? We could write a 1-bit equality comparator circuit. Well, we've taken a look at that before, and we want to compare here I1 to I0 to see if they're equal. Right down here, this is the canonical sum of products expression, but we also know that this is a representation for the XNOR gate because the XNOR gate is the equality gate. Right. And so if we were to write the circuit, right, so here's the same sum of products representation, right, same circuit from here to here. Right. I've labeled these output wires. So here's our first operation, I0 not ANDed with I1. I've labeled that wire P0. And then I0 not ANDed with I1 not is this operation. I0 ANDed with I1 is this AND operation. So the signal coming out of here is labeled P1. P0 and P1 are ordered together to be assigned to our output EQ. Well, if we wanted to go ahead and write this, right, with continuous assignment statements, here are our inputs, I0 and I1, our output EQ. Here are our internal signal declarations, P0 and P1. Right. Here I write assign EQ, the result of P0 ORed with P1. These continuous assignment statements are actually hardware. What this statement is doing, right here, P0 ORed with P1, is simply a representation of this OR gate, right? These are the input wires coming into the OR gate being assigned to the output. So that's a representation of just this part of the circuit. Here, when I assign to P0, not I0 ANDed with not I1, right? That's a representation of this part of the circuit. Here, when we assign to P1, I0 ANDed with I1, that's a representation, right, of this part of the circuit, this AND gate. The order of these continuous assignment statements is not important in Verilog. It will, from the way we write this, piece this together and form the same circuit in the same order of connection. Right. So with continuous assignment statements, the idea is the order of these is not important in the module. But now, if we try to do the same thing with an always block, so we have the same inputs, I0, I1, same output EQ. Instead of the internal wire types, we're having internal registers that are P0, P1, I call it REQ, right? We have to assign to the output wire the value REQ. REQ is going to hold, right here, what EQ held before. And then here, we're still going to have P0 and P1. So P0 and P1 are still going to have the same inputs, but now they're inside an always block, always at I0, I1. Well, remember, then whatever's inside this circuit is sensitive to changes in I0 and I1. These single equal signs are blocking assignment statements. Here, the order is important, right? It's not really important whether P0 and P1, the order of those two, but what's important is that both P0 and P1, these two statements must then occur, right, before this last statement where we OR things together. So by blocking, this means what's going to happen is this first statement will execute. Not I0 will be ANDed with not I1. That will be assigned to P0. When that is finished, then I0 will be ANDed with I1, assigned to P1. When that is finished, then P0 is ORed with P1, assigned to REQ. Right? As soon as there's that change on REQ, well, REQ is assigned back to the wire type here, and we get our output. Like I said, this is not a good way to write an equality a one-bit equality comparator, right? The best way would just be the continuous assignment statement with the XNOR gate. That's the fastest way. Like I said, this was just an illustration of the importance of order. What I would encourage you to do is to go ahead and put this in our Quartus software, right? Put it in a circuit simulator. Go ahead and put this in correct order, see that it works, change the order, see that it doesn't work. Right? So just keep this in mind. Remember, these are blocking assignment statements. Order is important inside an always block. Right, now, if statements. When do we use if statements? We use these, we're going to use if statements and case statements inside always blocks. So the if statement syntax says if Boolean expression. So this is an expression in here that evaluates to true or false. Whenever this expression inside this if condition evaluates to true, it will execute the code that belongs to the if branch. You can have an else statement. Basically, this says if true, do the things inside this begin and end, and then skip over anything in the else branch. Right? It's a mutually exclusive true or false condition. If true, do the following, skip over this stuff. If this is not true, if this is false, then if you have code in an else branch, it will execute the code here. So code inside an else branch only executes when every test above it has been false. Right? And so let's take a look at some examples. We need to know what we can use for relational operators. So by relational operators, those are the operators we're going to use inside here for these Boolean expressions. So these relational expressions. So logical negation is the exclamation mark, right? It's very similar to the complement. Right? If you say something's true, not true is false, not false is true. So it negates things. Right? Logical AND works very similarly to your AND gates, right? All of the inputs have to be true in order for the output to be true. So if A is true and B is true, then your output is true. If A is false and B is true, your output is false. Logical OR works very similarly to the OR gate. Any one of your inputs can be true, then the output will be true. All of your inputs have to be false in order for the total expression to be false. So greater than symbol, well, that performs then a greater than comparator, right? Less than symbol, less than comparator. Greater than or equal to, less than or equal to. Equality, so your equality comparator is represented by two equal signs, not one. One is assignment. So two equal signs to compare if A is equal to B. And that is the equality operator that we've learned to make out of logic gates. And then inequality not equal to. So number of operands means, right, we have to say if A is not equal to B. So A and B would be operands, you need two. So logical and bitwise operations are a little bit different. So remember, bitwise, if we have multiple bits, does a pairing of each bit and performs that gate operation on there. Right? So let's say that A is a 1-bit signal and B is a 1-bit signal. A and it with B, so this is your bitwise operator, perform. Your output is a 0. A ORed with B, there's your OR gate, your output is a 1. A and it with B, this is your logical, so there's two of them for your logical. Well, 0 is false, B is true, so your output is still a single 0, right? But the way we use it is considered to be false, so think of this as false. A ORed with B, so this is your logical OR, right? This is true. 0 ORed with 1 is true. So these work, the logic works just like the gates that you know, but you have to think of any of these logical outputs as being a single bit output, not a multiple bit output, a single bit output. And think of them as being true or false, where 0 is false, 1 is true. Because in this case, when A is a 3-bit signal and B is a 3-bit signal, if you have A ANDed with B, it does an ANDing of the pairs. It says 0, right? The least significant bit of A ANDed with the least significant bit of B. This middle bit of A is ANDed with the middle bit of B. This most significant bit of A is ANDed with the most significant bit of B. Well, for the A ANDed with B, A ORed with B, right, we get 3 binary zeros. For the logical operations, well, 0 AND with 0 gives us a false, right? 0 OR with 0 gives us a false, right? Now, if A is all zeros and B is 0, 0, 1, what happens is for A ANDed with B, right? This says 0 ANDed with 1. Well, that gives you a 0, right? And the zeros ANDed with 0 give you these zeros. So the result of A ANDed with B in this case would be 3 zeros. The result of A ORed with B, it does this bitwise pairing. 0 ORed with 1 gives you this 1. 0 ORed with this middle 0 gives you the 0. Most significant 0 ORed with the most significant 0 gives you this as your most significant 0. See, what I'm telling you is to be very careful. If you're working with an if statement and you're trying to compare A and B, you use these sort of relational operators. You do not use the bitwise operators. There are times that using them incorrectly will get you in trouble. Other times it won't. But if you learn to use the logical operators when you should, when you just need to know if some condition is true or false, we use these, right? And so we'll see examples of how to use these, right, in the future. All right. There are other operators we can use inside of always blocks. The tilde is the NOT gate, plus is addition. There's an at. So plus is the plus sign, make it number a positive. Minus is the minus sign by unary, right? That means there's only one operator that comes after that. This is your logical NOT. Here, this is exponentiation. Multiplication is the single asterisk, / is division. The percent sign is a remainder or modulus operator, right? We are not going to use these at this point. They have levels of precedence. What we will probably be using is the equal sign and the not equal sign. So as we use some of these, we will come back and talk about precedence, right? Precedence means, right, highest precedence means these operations would happen before these. So if you have multiple operators in the same statement, you need to know the level of precedence, or you can use parentheses always to force precedence. All right, so here's again our 1-bit equality operator, right? Same truth table we've seen. We did this little intermediate steps here. This shows what your intermediate output is with the P0 and the P1. Right. So this is what we've seen before. Right. So if we wanted to then, instead of implementing this logic, if we wanted to write a Verilog always block that wanted to check to see if A is equal to B, we can actually use this equality operator. Right. So we've got always at A and B, so our circuit is sensitive to changes in A and B, our output's EQ. Here's our begin and end block. We say if, and so this test condition goes inside parentheses. If A is equal to B, so double equal sign for the logical equality operator. If A is equal to B, then we want our output to be a 1-bit binary 1. Our output in this case is a reg type, because remember, inside an always block, any signal to the left of an assignment operator has to be a reg type. So this reg type here, we assign it a value of 1. So if this is true, we say REQ equals 1. Whenever this condition is true, it does not execute anything associated with the else block. If this condition is false, then it comes down here. So this says if true, do this. Else, if this was not true, go ahead and do this, which would say they're not equal and assign a value of 0. Right. And so here, this is called behavioral modeling because we're actually implementing a 1-bit equality comparator simply by using this set of relational operators here. Right? We don't have to worry about the logic gates. We just said, here's the behavior we want you to check. You go ahead and you form the circuit hardware underneath to do this. All right. Same thing, we can implement a multiplexer, so a 2-to-1 mux. Right, we have for 2-to-1 mux, we have 2 input lines, we have 1 select bit, we have a mux output, right? Our reg type is our mux out. We're going to assign our mux out to the wire type. mux out inside our always block. Now we're sensitive to 3 signals, I0, I1, and S. We say if our select bit is a 1, and actually this should be a 1-bit binary 1. I should really fix that. Let me fix that. See, sometimes I forget when I'm writing. If S, because S is 1 bit, right? If I just had the 1 all by itself, it forms a 32-bit number. Let's just be safe and compare 1 bit to 1 bit. So if S is a 1-bit binary 1, we want to assign whatever's on line I1 to our output. Else, if S is not a 1, well, the only other thing it could be is a 0, right? We're going to assign I0 out. We also could have written this code to say, hey, if S is equal to 0, assign our mux out I0, right? You can choose whatever comparison you want to implement, whatever order you want there, right? Whatever sort of logic, right? So that's how we write a mux. And what you should remember with behavioral Verilog is when you use these if-else statements, they do form a mux. So that is what the hardware will synthesize too. All right. You can cascade multiple if conditions. So if you have multiple conditions to check, then we say if Boolean expression 1. So if this expression is true, go ahead and perform the operations in here, skip all these other operations. Else if, so if this test condition is evaluated and found to be false, if you have an else if branch, then it checks this test condition. If this test condition is true, it performs the operations in here, skips everything underneath. Right, so if this is true, do this, skip everything else. If this is false, it goes down here and checks this. So else if this is true, do this stuff. Well, if this is false, it will go check if there's another else if, it will go check that. When that branch is true, it'll perform that, skip over everything else. The else statement only executes when every single test above this is false. And we never have a test condition with an else because the else branch only ever executes when every other test above it has been false. Right, so if you have multiple things you want to check, you then use this if else if condition or structure. All right, finally then on case statements, our last Verilog topic, right? We took a look earlier at how to use a case statement. Syntax is case parentheses. Inside the case is what signal we want to evaluate. We list our possible case values out here to the left, followed by a colon, and then one statement, or we can have multiple statements to the right. If we want multiple things to happen when that case is true, we can do that. We put them between begin and end blocks. And you can also have a default statement, right? A default statement says, right, if you haven't listed all of your cases here, let's say we have something that has 6 cases, and for 4 of them, we want the same thing to happen. So we might just list case 1 and case 2. And then by default, if our signal we're evaluating is neither case 1 or case 2, go ahead and perform this action. And then the case statement has to end with an end case. Right? So you don't always have to have a default. A default is something you can put in there if you need. Right? All right, we already took a look at this circuit, right? Our XOR, this is what we did earlier, but here it's called X and Y. Our mux we can write with a case statement, right? So the way the mux behaves, we've got 2 data input lines, a 2 input to 1 output mux, 2 data input lines, so data in, bits 1 and bit 0, right? Select bit, output M. We've got our reg signal that I've named RM, always at data in or select. You can separate the list by commas. You can also have an or inside the list. It's up to you. I'm showing you some different ways to do it. So like I said, if you look up examples, you might see this and wonder about it. All right, so whenever data in changes or select changes, it's going to activate this circuit. And right, we want to evaluate select. Remember the mux, the output of the mux is dependent on select. So we're going to evaluate the select signal. When select is a 1-bit binary 1, well, whatever's sitting on data input, whenever the select value is a 1-bit binary 0, whatever's sitting on data input 0 flows through to the output. When select is a 1, whatever is sitting on data line 1 flows through to the output. Right. So when we write a mux in this way, as we took a look at in the mux lecture video, this actually will form a case statement, forms a decoder, which actually then piped it into a mux. We have to remember to always assign the reg to the wire type. All right, so there's a way you can write a mux with a case statement. Like I said, it makes more sense to write a mux as a mux to use if and else, because we know that if and else, we've learned that that forms a mux. But I'm just showing you some different examples with circuits that you've seen before, right, to show you how you could write those, to show you how to use the syntax to do that. Here's a decoder, 2 input to 4 output decoder. Right? Yeah. If you've seen the decoder lecture, you've seen this circuit as well too. You need to know the decoder truth table for that. Well, an active high 2 to 4 output decoder has a unique set of ones, and it's based on then this 2-bit input, right? A. So we can say always at A, case A. So we evaluate A. When A is a 0, our output RD should be this binary pattern, this 4-bit binary 001. Right. Whenever A is a 1, our output should be a 4-bit binary 0010. Right. We know the way a decoder works, right, is when the input is a 0, an active high decoder uniquely has a 1 in the 0-bit position. Right. An active high decoder, when our input's a 1, has a 1 in the bit 1, 2 to the 1 position. Right. When our input's a 2, it has an active high in the 2 to the 2 position. When it's a 3, it has an active high in the 2 to the 3 position. Right. So this is how you would do a 2 to 4 decoder with a case statement. So just to give you an example. Right. And that is our last slide in this lecture. Like I said, this is more or less than to have talked about the syntax of a language. Right. So to give you more ideas on how you should properly use it. So have fun creating some circuits. I would create some of these, simulate them, right? See what kind of hardware it gives you, and gives you practice using the syntax and understanding how to write these. Right, thanks for